As you can see in this video, we're going to take a look at position, velocity, and acceleration and how they are related to one another. In problem number 1, the graph shows the position. So that's the first thing I want to pay attention to, is that I am answering all of these questions based on the fact that I'm given a position function. I always like to write that on the graph so that I remember what kind of function I'm looking at, because the function I'm looking at will determine how I think about and figure out how to answer these questions. This particle is moving along a horizontal axis. So the particle, maybe this is our particle, it's moving to the right, and then maybe it goes back to the left, and then it goes back to the right. So basically the point or the particle is moving along a line, and it's indicated by its position given on this graph. The position is measured in inches, and the time is measured in seconds. Question A, when? Okay, so the first thing I have to do is decode the question. They're looking for a time. When is the particle moving to the left? So what do I think about on a position graph when I'm looking for, in this case, the particle moving to the left? So for moving to the left, I am looking when the position function moves down, or when the position function is decreasing. So the position function is decreasing on this interval right here. So from 0 to 2, it looks like the particle is sitting at 4 inches, and then the particle begins to move, and because the position function is decreasing, the particle is moving downward on the interval from 2. Notice that that is an open interval, to 4, and that's an open interval. So at those intermediate points, we generally do open intervals on the intermediate points, and we close on the endpoints. Question B. When, okay, so we're looking for time again, is the particle moving to the right? So particle moves to the right when the position function is increasing. So I'm looking for all increasing intervals, and so the particle is increasing on this interval right here. From 6 to 7, the particle is constant again. So the particle is moving to the right on the interval from 4 to 6. And again, those intermediate values are going to be open intervals. When is the particle standing still? So for the particle standing still, in other words, that when is S of t constant. So this is what I'm thinking about and trying to figure out when I'm looking at the graph. So the position is constant from 0 to 2 and from 6 to 7. So on the end point of 0, I'm going to close it or bracket it. So 0 to 2, open. And then again from 6 to 7, and I'm going to close or bracket the endpoint at 7. That's the time at which the particle is standing still, no movement. For letter D, we are looking to graph the velocity. So I have to remember that the derivative of position is velocity. That's my thinking. So derivative is instant slope, or we can think of slope. So I want the slope of position. I want it to describe what's happening with the slope, and that will give me the instant velocity. All right, so I'm going to erase my annotations back up here on the graph so that I can, if my eraser, there we go. So in the first region, I can see that the position is constant and the slope is constant. In other words, I have a horizontal segment, and the slope of that horizontal segment is 0. So from 0 to 2, I'm going to put a closed circle on 0 and an open circle on 2. The slope is 0. So I'm literally just showing or describing or indicating what the slope is of that segment from 0 to 2. For the next region, from 2 to 4, you can see that I'm going to, this is because these are linear segments, I can just do rise and run. So in this case, I'm going to drop from 4 to -4. So that's a drop of 8. So -8 down 8. and I'm going to run from 2 to 4, so that's a run of 2. So the slope is -4 of this line segment right here, and that goes from 2 to 4. So 2 is open. Here's -4 down here. 4 is open. So the other thing we got to remember is that wherever there is a sharp turn, the derivative is not defined. So the left and right derivatives do not agree with each other at x equal to 2, x equal to 4, and x equal to 6. So that's the support of those open circles. Then we want to go to the next line segment, which is from 4 to 6. Since the position function is increasing, the slope will be positive. So I am rising from -4 to -2. So that's a rise of 2 and a run of 2. So the slope is 1. So that's going to be halfway in between. So from 4 open to 6 open, my slope is 1 of that segment right there. And then finally, the last segment, we can see right here that the slope is constant, and we have a horizontal slope. The slope is 0 from 6 to 7. So open at 6, closed at 7, and that is the graph of the velocities or the slope of the position function. That's letter D. Letter E simply wants us to create a speed graph. I'm not going to recreate everything, but let's talk about what speed is. Speed is no one's derivative. Speed is the absolute value of velocity. In other words, it is the velocity without its sign. So if we take the absolute value of velocity, all of the values are going to be positive. So really the only thing that's going to happen is this segment that is below the x-axis is going to reflect over the x-axis, and it's going to reflect up to here to +4. So I'd have from 2 to 4. And so the speed graph would be from 0 and above, and that's what my speed graph would look like. So this piece would be gone for the speed graph. So that's how you change the velocity graph into a speed graph. And then finally for letter E, for the particle moving fastest is when is the speed the greatest. And remember, I just created a speed graph, so I can easily look at the graph and see that the speed is the greatest from 2 to 4 because that outputs a y value of 4. So from 2 to 4 is when the particle is moving fastest. All right, let's look at the next page. And I want you to contrast that. On the first page, we were looking at a position graph, but now we are given a velocity graph. So I call it the Etch-a-Sketch move. You kind of have to shake your head a little bit and clear out the way you were thinking about the graph before, because now we have a velocity graph. So we're going to have to think differently about how we answer the questions. And remember that velocity is the slope or the instant rate of change of position. We also know that velocity, just as a review, indicates two quantities. It indicates speed, which is simply how fast the particle or object is moving, and direction. And the direction of the particle is indicated by the sign of velocity. So we're truly just looking at whether the sign is positive, and that would mean either upward movement or to the right in a positive direction, depending on the context of the problem, or negative would indicate a backwards movement or falling, or again, depending on the context of the problem. So here we go. When, that's looking for a time, does the particle reverse its direction? So in other words, that would be, again, the particle is moving along the horizontal axis. So again, the particle is just moving back and forth from right to left, left to right. So the reversing directions would be when, this is what we're looking for, when v of t not equals 0, but changes sign. There has to be a sign change in order to have a reversal. So I know that the velocity is 0 at t equal to 1. I know that velocity is 0 at t equal to 2, 3, 4, a little bit more than 4. Let's call it, let's just call it 4 to make it easy. I know it's not exactly 4, but we'll fudge it and say it's t equal to 4. So the question is, does the particle change signs? Well, from 0 to 1, the velocity is positive because the graph is above the x-axis. And from 1, whoops, I meant to change colors. From 1 to all the way to, looks like 3, the velocity is negative. So yes, there is a sign change. So the particle reverses its direction at t equal to 1 and t equal to 4. Again, what you're looking for is a velocity change of sign, and that happens here. All right, let me clear the graph or erase my annotations on here. It's getting a little bit messy. Letter B. When, looking for the time, is the particle moving at a constant speed? Now this is a velocity graph, but remember speed is a component of velocity. Now don't look at the slopes of this graph. So let's talk about that first. The slope of velocity, when I say slope, I'm talking instant rate of change. The slope of velocity is not speed, which students often get. Students, when you're first learning this, regardless, speed and acceleration often get confused with each other, or some people think they're the same. They are not the same. The slope of velocity is, or takes me to the acceleration. So I don't want to look at the slopes. I just want to look at when the velocity function isn't changing. So we can see from 0 to all the way, I mean the slope is changing, I mean not the slope, the velocity, sorry, graph is changing. The velocity graph remains constant from 5 to 6. So the speed is constant from 5 open to 6 close. Next question. When does the particle move at its greatest speed? Now again, this is not a speed graph. It is a velocity graph. So what I'm looking for the greatest speed is the greatest magnitude or distance from the x-axis. I mean, yes, I could take the absolute value of this graph. I could reflect this piece that's below the x-axis above and create a speed graph. But really, I'm just trying to figure out when is the velocity graph at its greatest magnitude or distance away from the x-axis. So I would say my candidates are here. I have a y value of 2. Down here, I have a y value, it looks like -3. And up here, I have a y value of 2. So I think those are the times at which the velocity graph is at its greatest magnitude, but it's at the very greatest when we hit down here at -3. So I would say, when is the particle at its greatest speed? It's at its greatest speed at t equal to 3 seconds. I think it's seconds, yeah. And I should have seconds here and seconds here. All right, the next thing I'm going to do is graph the acceleration. And remember, we had that conversation that acceleration is the slope of velocity, not speed. So if we're going to do the slopes again, I'm going to look at the first region, and I can see that the graph is a linear line, or a linear segment, or a segment from 0 to 2, and there's a change at 2 of slope. So this is going to be a drop of from 2 to -2, so that's a drop of 4, so I have -4. And we're going to go from 0 to 2, so that's a run of 2. So the slope of that first line segment is -2. So from 0 to 2, -2. All right, so 0 is closed, endpoint, to 2, open. The slope of that segment is -2, meaning the acceleration in that region would be -2 meters per second squared. the next region, the next little segment is from here at 2 to 3. So we're going to drop 1 unit, so that is down 1, and to the right 1. So that slope is -1 from 2, open, to 3, open. And that would be the acceleration of the particle in meters per second squared from 2 to 3. The next segment goes from 3 to 5. So we're going to rise from -3 to 2, so that's a total rise of 5. And we're going to run from 3 to 5, so over 2. I think I counted that correctly. Yep. And so that's going to be 2.5 or 2.5 from 3 to 5. So here's 3. 2.5 is about right there. To 5 is about right there. Open circles. Okay, so that's the acceleration in that region. And then in the last segment, the slope of that horizontal line segment is 0. So from 5 to 6, 5 is open, 6 is closed. The slope is 0. So spend some time paying careful attention to the difference between how you read the graphs and get your information. One more question. A particle moves along a vertical coordinate axis. So now the particle is moving up and down and up and down and up and down because it's a vertical coordinate axis. So that it's positioned at any time. We're given a position function right here. This is not necessarily a free-falling object, where S is measured in centimeters and T is measured in seconds. I want the displacement of the particle during the first 6 seconds. The definition of displacement, which is not necessarily the same thing as distance, is change in position. That is the definition. So we go to the definition to figure out what to do. Change in position can be written as delta S. So it's not a slope, or we can think of it as terminal position minus initial position. So in this case, our position function is S. So we would want the terminal position, which is S of 6, minus S of the initial position was 0. And that would be measured in centimeters because it is a position. I'm not going to actually do the calculations. You could use a calculator to calculate those numbers, but I'm more interested in talking about how would we do that, or how would we answer that question. Letter B, we are looking for the A for Algebra 1 average velocity during the first 6 seconds. So average velocity is based on that old idea of, we talked about, we kind of introduced with this, distance is equal to rate times time. So rate is equal to distance divided by time. That's our old middle school idea. So average velocity is equal to change in position over change in time. So in other words, it is the displacement, it's the displacement, which is change in position over the change in time. So in this case, that would be S of 6, which we did in the first part, minus S of 0. If you calculated that number, you could use that, over 6 minus 0. That would be our difference quotient. And since this is velocity, it would be measured in feet per second. Again, you can, if you want to, you can use your calculator to calculate that, but right now I'm more interested in how would you do that problem. All right, I'm going to clear my annotations so that I have room for, actually I can do it over here on the side. So let me create a little bit more paper here. There we go. Delayed reaction. All right, let's move that back up. So, get this out of the way. Okay, my pen has decided to go crazy view. Let me get my pen settled here. So for letter C, find expressions for the velocity and acceleration. So notice the word the velocity and acceleration. So the is indicating instant. So we want instant rate, which is derivative. So using the power rule, the position function on the position function. The derivative of the position function would be t squared. And by the way, I'm looking back up here if you're wondering where I'm getting this from. I'm just using the power rule. So t squared minus 6t plus 8. That would be the instant velocity. And that would be measured in centimeters per second. And then the acceleration function is the derivative of velocity. Using the power rule, I get 2t minus 6, and that would be centimeters per second squared, because we're dividing by centimeters again. And then lastly, letter D, for what values of t is the particle moving downward? So remember, we have to think about what is the best function to use for particle movement. Now, I do not have a graph of position. If I had a graph of position, I would just look at the graph and determine when the particle is moving downward. So since I have calculus, remember we can use velocity. Let's just keep pounding that idea back in. Velocity shows two things. It shows speed and it shows direction, which is what we're after in this question. And direction is determined by examining the sign of velocity. So in order to determine the sign, the first thing I'm going to do is I'm going to figure out, well, when is the velocity equal to 0? And then I'll make an examination. So I'm going to do t squared minus 6t plus 8 equal to 0. Good old quadratic. I'm going to factor that, t and 4 and 2 and minus. So at t equal to 2, the velocity is 0, particles not moving. And at t equal to 4, the velocity is 0, particle not moving. But that's not what the question asked. The question said, when is the particle moving downward, not when is the particle not moving. Well, I'm going to organize my information onto a number line. I'm examining the velocities, and I care about the sign of velocity. I'm going to put t equal to 2, which is velocity 0, and t equal to 4, velocity 0. So I now have 3 regions that I want to test, and the problem says the particle started moving at 0. So at that end, we're closed, and then we're open on the other end. I think it just kind of opens it. So I'm going to choose a value in each region. So in region 1, I'm going to choose a t value of 1, and I'm going to substitute that 1 into the velocity function. So when I do, I'll get 1 minus 6 is -5. -5 plus 8 is 3. So 3 is a positive output. Therefore, the particle is moving upward in that region. Velocity positive, particle moves upward. From 2 to 4, I'm going to choose a t value of 3 and substitute it into the velocity function. So that would give me an output of, actually, if I substitute in here, it'll be a whole lot easier. So 3 minus 4 would give me a negative. 3 minus 2 would give me a positive, and a negative times a positive is a negative. Particle moving downward. I'm going to choose a number greater than 4, like t equal to 5. I'm going to substitute into my factored form. 5 minus 4 is 1, which is positive, times 5 minus 2 is 3, which is positive, and a positive times a positive is a positive. So I can now see that the particle is moving downward from 2 to 4. So spend some time with this. Very important concepts.